Welcome back, guys. This is day 2 of our statistical, I can never say that right, statistical research project. Um, and this part that we're going to be talking about today is a grade. So once you figure out your research team and what you're going to be researching, this piece that you're going to be putting together is going to be turned to me, and it's going to be informative for your for this unit. So this is also the very front page of your notes. So we're going to first start off talking about data collection. And once you figure out a research question, which is what we talked about earlier, the next phase involves data collection. So how are you going to collect your data? This involves collecting the necessary data to test the null hypothesis, which we briefly talked about yesterday, which is saying there is no difference in what you are studying. Through various methods such as surveys, which you guys have done 2 of already, experiments, which you haven't done yet, and observations. The method chosen often depends on the research question and the nature of the variables involved. So we're going to look at first an observational study. This is a type of study where the researcher watches and records what people do or what happens in nature setting without trying to change anything. In these studies, researchers gather information about subjects such as behaviors or conditions to identify patterns or relationships. So you're not really doing anything except observing. An example of this is if a researcher wants to learn how eating breakfast affects students' grades, they might observe a group of students over time, noting who eats breakfast and how well they perform in school, but they don't tell the students to eat or skip meals. They don't interfere at all. They just let them go about their daily lives, and this allows them to see the effects in a real-world context. The other type is something that you guys have already done twice. A sample survey is a research method used to gather information from a sample in order to make generalizations about a larger population. Researchers design questions to help them find out people's opinions, behaviors, or characteristics. It's important to note that your sample should be representative of the larger group to ensure results are accurate. So we always want to make sure when we're collecting data that it goes along with our proposal. Like, what are we initially, our research question, what is that trying to answer? Who's our population of interest? And our sample needs to represent that population of interest. And I don't think I said this in the last video or probably maybe in class, but I mean, if you are looking at, for instance, the heights of males, then your population does not include females because you're looking at the heights of males. Um, so so your samples should not include females because you're looking at the heights of males. That's kind of what that is stating. Um, an example survey, if you want to know what high school students think about school lunch options, you might survey students from different grades and backgrounds to get a well-rounded view. And it's often noted that when you think about these different types of studies, you do want to have some type of diversity between like what it is you're doing, and obviously strive to get a random sample. Um, and a random sample is going to be included in a survey or an observation or the last thing that we're about to talk about. And that helps you get more reliable results. The last type of study we're going to look at is an experimental study where researchers manipulate one or more variables to observe the effect of participants' responses or behaviors. This type of study allows for the establishment of cause and effect relationships. Now, we're not going to be doing like a more than likely you're not going to be doing like dividing people into groups. But we can still manipulate some things. Some of the experimental things that I have on the list involve like blind taste testing, where you are manipulating like sight. So you kind of take away like what you see, and you still do some type of manipulating, but it's not going to be so much um, where you're putting group A and group B, and one group has placebo and the other. It's not like that. Now, you may have something like that, but chances are you probably won't. An example of this is a researcher wants to know how different amounts of sunlight affects plant growth. They can set up an experiment where they grow plants with varying sunlight exposure and measure their growth. So just an experiment exactly as it sees, or exactly as it looks. I'm going to see if this works on this video, and I'm going to go ahead and play this.
Scientific practices in order to improve them. This field has emerged in response to a crisis in science, and p-hacking is just one part of that crisis. So what's going on, and can we fix it? Learn more with this video.
Oh, sorry. Let me...
In 2011, a group of researchers conducted a scientific study to find an impossible result, that listening to certain songs can make you younger. Their study involved real people, truthfully reported data, and commonplace statistical analyses. So how did they do it? The answer lies in a statistical method scientists often use to try to figure out whether their results mean something or if they're random noise. In fact, the whole point of the music study was to point out ways this method can be misused. A famous thought experiment explains the method. There are 8 cups of tea, 4 with the milk added first, and 4 with the tea added first. A participant must determine which are which according to taste. There are 70 different ways the cups can be sorted into 2 groups of 4, and only one is correct. So, can she taste the difference? That's our research question. To analyze her choices, we define what's called a null hypothesis, that she can't distinguish the teas. If she can't distinguish the teas, she'll still get the right answer 1 in 70 times by chance. 1 in 70 is roughly 0.014. That single number is called a p-value. In many fields, a p-value of 0.05 or below is considered statistically significant.
Sorry, I'm gonna pause this real quick. We'll talk about the p-value tomorrow and the next day, and also some of this other stuff. But I wanted to show this video just to kind of explain some of the parts that we're going to be looking at as we move forward. So let me continue to play this.
Meaning there's enough evidence to reject the null hypothesis. Based on a p-value of 0.014, they'd rule out the null hypothesis that you can't distinguish the T's. Though p-values are commonly used by both researchers and journals to evaluate scientific results, they're really confusing, even for many scientists. That's partly because all a p-value actually tells us is the probability of getting a certain result, assuming the null hypothesis is true. So, if she correctly sorts the T's, the p-value is the probability of her doing so, assuming she can't tell the difference. But the reverse isn't true. The p-value doesn't tell us the probability that she can taste the difference, which is what we're trying to find out. So if a p-value doesn't answer the research question, why does the scientific community use it? Well, because even though a p-value doesn't directly state the probability that the results are due to random chance, it usually gives a pretty reliable indication. At least it does when used correctly. And that's where many researchers, and even whole fields, have run into trouble. Most real studies are more complex than the tea experiment. Scientists can test their research question in multiple ways, and some of these tests might produce a statistically significant result, while others don't. It might seem like a good idea to test every possibility, but it's not, because with each additional test, the chance of a false positive increases. Searching for a low p-value and then presenting only that analysis is often called p-hacking. It's like throwing darts until you hit a bullseye and then saying you only threw the dart that hit the bullseye. This is exactly what the music researchers did. They played 3 groups of participants, each a different song, and collected lots of information about them. The analysis they published included only 2 out of the 3 groups. Of all the information they collected, their analysis only used participants' father's age to control for variation in baseline age across participants. They also paused their experiment after every 10 participants and continued if the p-value was above 0.05, but stopped when it dipped below 0.05. They found that participants who heard one song were 1.5 years younger than those who heard the other song, with a p-value of 0.04. Usually it's much tougher to spot p-hacking because we don't know the results are impossible. The whole point of doing experiments is to learn something new. Fortunately, there's a simple way to make p-values more reliable. Pre-registering a detailed plan for the experiment and analysis beforehand that others can check, so researchers can't keep trying different analyses until they find a significant result. And in the true spirit of scientific inquiry, there's even a new field that's basically science doing science on itself, studying scientific practices in order to improve them. This new field has emerged in response to a crisis.
Okay, so that's that. We'll talk about that more later, and it is it can be a little bit daunting, I guess, if you will. Let me go back to what I was at. But I'm going to kind of break this down with when we get into p-values tomorrow, in terms of like what I want you to say, essentially. But before we get started, let's look at a type of topic that we can look at to where we can do, like, maybe we're concerned with, your mom told you your whole life, make sure you wear your coat or you're going to get sick. So you're wondering if that's like not true, or if she's just saying that because she's your mom or whatever. How might you go investigate that with collecting data? Well, we're going to look at three different things involving the same thing, and these are three different ways that you can investigate this. So let's see if we can figure out which one is which as we go through. So on cold days, you record which of your classmates come to school without a jacket. Later, you record how many of those students become sick. That would be considered observational. You're simply observing. You're not interfering with any of the investigation. You're just simply watching. You have a sample of doctors complete a questionnaire about health risk involved with going out in the cold without a jacket. This would be a questionnaire that would be a sample survey. And then lastly, you find 30 adults and divide them into two groups. The first group is told not to wear jackets on cold days. The other is told to wear jackets on cold days. You then compare the number of each group who gets sick after a string of cold days. That would be an experiment. You are manipulating part of the study, of the sample. So for the remainder of class, obviously if you're watching this video, you're probably not here, but in class, for the remainder of class, you and your team of researchers need to complete your project proposal. Since I have taken up time in this class, I'm going to give you the rest of class today and all of class tomorrow. You need to make sure that you write your project proposal in complete sentences. This is a grade, and only one person from each group needs to bring this to me. This will be due by the end of class tomorrow.